down, in the front is free. And close your mobile. This is the fifth and the last plenary lecture for the 21st INQA Congress in Rome. And the speaker is Pradeep Srivastava. He's a trained sedimentologist and geomorphologist who has more than 20 years of working experience in the quaternary landscape of Himalaya and its foreland. His research has helped understanding the fluvial aggradation and incision processes as function of climate and tectonics of Himalaya and Ganga Plain, and the past and present extreme hydrological events in the Himalaya. He has published over 100 research articles from across Northwest and Northeast Himalaya. He serves as an associate professor at the Indian Institute of Technology at Roorkee. Pradeep is a member of International Science Steering Committee of Past Global Changes and is a recipient of J.K. Gilbert Award of AAG. He serves on the editorial board of INQA flagship journal, Quaternary International, and also in Journal of Quaternary Science and Paleo 3. He is vice president of the Association of Quaternary Research in India and is an elected fellow of the Indian National Science Academy. So it's my deep pleasure to introduce Pradeep and the title is Geology Floods in Himalaya.
Thank you very much, sir. And I am honored and delighted to be here. I thank INCWA for inviting me for this talk. And the title I have chosen for my talk is The Geology of Floods in Himalaya. The reason being that this region serves more than 1/5 of the human societies, human civilization on the earth. And it remains very volatile all through the years and decades. And I dedicate this talk to the fond memory of my good friend and very eminent Himalayan geologist, An, who just I came to know about this morning that he lost battle to life this morning. The talk was uploaded yesterday, so I do not have any slide for dedication. So I begin here. The slide which you see in the front comes from the headwaters of Ganges. And this event, which it signifies, is 2013, when the millennium's largest flood occurred, hit the Himalayas, and around more than 6,000 people lost, and around similar amount of lives were lost. I mean, they were we were not able to trace them. And it's now 10 years. The government of India has now declared them dead as well. So the total loss of life was around 12,000 people. So I also dedicate this talk to all the lost lives in Himalayas to this event. And I'll try to impress upon in the next half an hour that geology of Himalaya actually plays a very important role in deciding the locus where the damage will occur. So there is a sense of predictability, and we geologists can play a very important role in providing the damage zones or predictable damage zones to the society when it comes to case of such large magnitude floods. You see, the global flood risk, it is the global south. I mean, these are the projected regions which will face the maximum flood frequencies, higher flood frequencies. And globally, you see that it's a staggering around $105 billion of world economy we lose every year just because of floods. And this is the projected mortality in the global south. And this basically happens because of the lack of inflow of knowledge, lack of resources, and lack of empowerment. We are here, and it's our great responsibility, our biggest responsibility, that we see these happy spaces to remain empowered for the rest of their lives. See that Himalaya actually hosts somewhere around 6-7 major river systems: the Indus, the Ganga, the Brahmaputra, the Yangtze, the Amur Darya, and partly the Yellow River. And that serves around, as I said, around 20% of the humanity. And that's the reason I say that anything that happens in Himalaya has a ripple effect, if not dent, the global economy and global humanity. In the times when we have these things, global supply chains, fragility of global supply chains, wherever anything happens, we cannot remain aloof and remain silent. It disturbs the whole world, it disturbs the whole society, and it disturbs the humanity. So we need to work closely, we need to generate models that are universal in nature and that help the human society. With these, I have few major questions on my mind that in few slides, I'll try to answer. What is the natural climatic ramp that induces higher flood frequencies in Himalaya? What controls the magnitude of floods? Where are the hotspots of damage? Where are the hotspots from where the maximum amount of sediment is being produced. So with this motivation, the structure of the talk will be flood disasters, millennium as mapped, geology of floods, geological controls of flood magnitude, past flood records from Indus and the Brahmaputra, climate controls on flood and human migration, erosional hotspots, and then I'll conclude. You see, Himalayan arc is a result of plate-plate boundary collision, where Indian plate subducted below Tibet, and it made an arc, Himalayan arc, that has a radius of around 1,600 kilometers. And because of this thrust tectonics, you see that it forms a thrust, and it follows the Coulomb wedge model, where the frontal thrust remains active, and the thrust at the back locks and remains inactive. Because of this thrust and fold belt tectonics, it forms a typical orography. This black, you see that this is the Ganga river system, and this is the south profile. The black one is the geomorphic profile, and blue one is the rainfall profile across this region. So because of this thrust tectonics, it has a typical orography, and we have first rainfall high just encountering the mountain front, and the second rainfall high coincides with from where the mountains actually starts picking the elevation. So these are the two physiographic transitions, physiographic transition 1 and 2, and you see that rainfall reaches up to around 2,000 millimeters or around 3,000 millimeters, and then it diminishes. So this front is called Southern Himalayan front, and the front in the north is called as Northern Himalayan front, which remains dry and remains in the rain shadow. And this is how the whole structure is. We have several thrusts, Himalayan frontal thrust, main boundary thrust, and main central thrust, and in between there is a big crystalline body that is called as the core of the Himalaya, and that extrudes because we have decompressional melting below the Tibet. As the Tibet collapses, it decompresses and we have melting, and because of the erosion at the mountain front, it forms a channel. So it's a channel flow model that it forms, but it has a coupling with the surface processes. And this is the mountain front, the growing mountain front, and the smaller mountains and the bigger mountains or higher mountains at the back. This is 2013 event, and this image, the bridge lies somewhere around 70 meters above the riverbed. It's now, in 2013, it was completely covered with the flowing water. Important thing to note is that these waters are not only the waters that has 1 gram per cc of density. These are laden with sediments, and that has a very huge, large amount of gram per cc density. And these waters are, they can roll the boulders as large as room-sized boulders. So they have energy to topple anything that comes in their way. And this is what happens in the way. All the buildings and everything, they were just washed away. And this happened in 3 days of time, 16, 17, and 18 June of 2013. Another important thing to notice that in mountains, you'll see that most of the roads are winding. So pre-event, there are 5 winds, and post-event, 2 of these winding bends were buried. And this amounts to 29 meters of aggradation. 29 meters of aggradation in 1 event. So just imagine the amount of sediment it transported from the headwaters to the downstream. And it also didn't, whole of the Gangetic plains in front of this were completely flooded. So more than 6,000 lives were lost, 200 million worth of dollars economy was lost, 3,000 landslides were activated or reactivated, more than 1,000 government buildings and civil infrastructures was lost. Whole of the civil infrastructure that was built post-colonial era was actually failed, and we have to deploy Air Force to evacuate the people. So this was the largest ever human evacuation, air evacuation in 2013 that India witnessed or India managed. So this is the catchment of Ganga. After this event, I took a team of 20 students to the mountains just to show them that what happens after the disasters of this magnitude strike. They had their mobile phones, they had their GPS, and they just managed to get the location, and we were there together of all the landslides and for all the buildings that were damaged. With doing cluster analysis, we found that there are two major clusters of landslides and two major clusters of building damages. And these two clusters just overlie on the physiographic transition 1 and physiographic transition 2. Thereby, the stress is that these two damage zones are basically controlled by the geology of Himalaya, which, in my view, are predictable. We as a geologist, we know that what's happening. You see that this is the Indian plate subducting below the Tibet. So it has a ramp and flat geometry. Flats are where the topography of the subducting plate is around 4 degrees, and ramps has around 12 degrees. So wherever you have a steeper ramp, the riding plate will have more friction, and that's how it forms a duplexes, and that's where you rise the topography. So that's where you have first physiographic transition here and second physiographic transition just lying here. So whatever the damage you saw in those two clusters is basically controlled by what is happening 10 to 20 kilometers below the surface. And this is very much mappable using any kind of geomorphic indices that helps you in understanding the river systems. Any geophysical technique that helps you in understanding the subsurface geology. And that's where I'm saying that probably we are in position to map ahead a priori where the damages will occur if the event of such kind strike in mountains like Himalaya or anywhere. It may be Appalachians, it may be Rockies, it may be Apennines. So if you have these kinds of tectonic settings, if you have this kind of orographic setting, damage zones are predictable. So this was the first lesson. Another thing which I want to stress upon is these natural disasters are disasters later, but they are natural processes. In past, when we studied all the major river systems in Himalaya, we found that post-glacial aggradation was actually driven by the debris flows and extreme events. And this occurred in a very short time. And these events actually built the landscape on which the human societies are thriving. So the floods are basically the landscape constructors. They construct the landscape on which we live, on which we survive, on which the A-class arable lands are formed. You see, this is a famous duo of Haim and Ganser. They were the famous Himalayan geologists in 1930s or so. In 1893, there's similar kind of event struck Himalaya, and a major landslide blocked the river called Birhai Ganga. It's a tributary of Ganges. And the lake survived for around 100 years. In 1970, similar event washed this lake, and this is the topography now. So this is in 1930, where the Haim and Ganser are having their lunch, and this is the modern topography. So everything in high relief zones is so dynamic, vertically. In the low relief zones, it is dynamic, not vertically, but horizontally. You see that all the alluvial fans, they build laterally. So they are dynamic in the high relief zones as well as in the low relief zones. In long term, similar flood deposits, similar flood events, they fill the foreland basins to the extent that it overloads the basin and it goes down, and the peripheral bulge in response goes up. So it decides the long-term tectonics of Himalayan fold and thrust belts also. So with these background knowledge, I started thinking that why not to explore the river systems across. So these are the humble sedimentary layers called as slack water deposits, and these are formed by a couplet of fine sand overlain by a clay silt. This couplet largely formed because in the rising limb of the flood, these sands are deposited, and the waning limb of the flood, this clay bed is deposited. So one couplet of clay and silt is called as one unit of flood, and it represents one flood event. It may not represent one season. In one season, you may have more than one flood events, right? So one sand silt couplet represents one flood. These are able to inform you on the structure of flood, means it was a debris flow, it was a flash flood, it was a glow, it was a regular monsoon flood. These sand silt couplets are able enough to inform you on these recurrence intervals. If you date these couplets, you can lay your hands on the recurrence intervals. And looking into the sediment characteristic, you can always talk about where they erode, and then you can model them and think what are the basic forcing factors of these major floods. These deposits are normally found at the junction of major rivers, where the smaller rivers join the larger rivers, and when these flood water rise, it goes into it. Wherever you encounter the zero velocity, these couplets are formed. Where you have the wider valleys, because the flowing water velocities are arrests all of a sudden, so most of the coarse sediments are deposited. They're also found on the rock benches above the river beds. So they also inform you on the area, on the level where the flood was risen. Fortuitous things on these, because the humans have been exploiting fluvial geomorphology or riverine geomorphology for their existence since ages. And on these floodplains, many a times, we find these baked layers where the early prehistoric humans actually camped and cooked their foods and had their existence. So these are the baked layers, which we call as hearths. In these baked layers and surroundings, you find these dung cakes, chewed bones, and often stone implements. So these floodplains, flood deposits also inform you on the human fluvial geomorphology interaction with time. Now, with this background, I'll take you to the tales of two major river systems that Himalaya has, and the two extremities. This is the western syntaxis, and this is the eastern syntaxis of Himalaya, and this is the Indus River that flows from Mount Kailash towards the west, and this is the Brahmaputra or Sangpo that flows from this place and cut across the eastern syntaxis of the mountain. If we just reconstruct the longitudinal profile of these rivers, because they are overlapping, you see this is the Indus, and this is the Brahmaputra. The important thing to note here is that Indus rises from around 5,000 plus elevation, but the Sangpo rises around 3,000, 3,500 meters and goes up to 2,500 plus. So this is the structure of the Tibetan plateau that actually dips towards east, right? And also, this Himalayan arc, it is the northern latitude, and it goes as you go towards east. It goes towards the equator. So northwestern Himalaya, it has higher elevation. Tibetan plateau is higher elevation, and eastern part is having the lower elevation. And another thing is that this whole region of Indus, upper part of the Indus, lies in the rain shadow zone. Most of the rain just appears here. Whereas in Tibetan plateau, part of the Tibetan plateau in northeast receives more than 1,000 millimeter of rainfall. And another thing is that this region is dotted by more than 1,000 live lakes that were formed after the deglacial melting, last glacial maxima. These kinds of lakes are there. So another thing is in this part of the catchment, rainfall never reaches, and in this part of the catchment, you have all kinds of ingredients that can produce the extreme events with large amount of sediments. So differences you can see in the sediments. These are the centimeters scale couplets in Indus. that inform you on the magnitude of the floods, whereas Indus is Brahmaputra or Sangpo is this. One flood event is represented by 20 meters of thick sediment deposit. So orders of magnitude difference in flood styles and flood magnitude is again controlled by the continental scale geomorphology and how it interacts with the charging air parcels or monsoon moisture parcels. Okay, so now I'll take you to Indus, which is, the topography is like this. It's truly a cold desert, around 150 millimeters of rainfall, and most of it is just sand rams and sand dunes and thin riverbeds. And this is the geomorphic topography profile, and this is the rainfall profile. So most of the rain just remains here. This remains in the rain shadow zone. The geology of this whole area of Indus is so that we have Indus batholith, Ladakh batholith, which is the arc granite, and it is around 100 million years to 50 million years old. And in south, this is the Indus. In the south of it, you have the Tethyan sediments and Zanskar sediments that are as old as 500 million years to 700 million years, and they come around up to Eocene or so, Upper Cretaceous. So if you see these deposits, there is an opportunity to understand that how much sediment comes from which part of the Himalaya. So what we did, we traveled all across Indus and traveled all across its tributary, southern tributary, to understand that which river actually is contributing to the volatility of the system. So these are kinds of deposits we look. This is the Indus and Zanskar catchment. These are the places where some sediments were located. And let me tell you, the chronology was established using the carbon-14 AMS on the charcoals. These charcoals, since they were produced in situ because of the hearth, they are not representing any catchment dynamics, so they were good enough to give us the dates. And some of the chronology was actually produced by using luminescence. In many cases, when you have more than 2 chronometers working, life becomes hell. But here, because they were in very good agreement with their basic premises, we could get the good chronology. You see that Indus, in this spot, had around 22 flood couplets, and it ranged from age from 13 Ka to 9 Ka. These are the net preserved deposits. So it doesn't mean that these are the only flood events, but these are the larger and larger flood events that are preserved. And using the basic Manning's equations, we could understand that the discharges in Indus at around early Holocene or the post-glacial optimum were around 6 times higher than the modern floods, right? So this is the information we get from Indus. Another that with southern tributaries, these are the thin couplets. Just don't get bogged with this. These are sand silt couplets, and we could record 27 events and 3 hearth events. So important thing to note is that from 9,000 to 6,000, these humans were again and again occupying the same spot for their livelihoods. And there are 27 flood events recorded in the early Holocene, early to mid-Holocene. In the lower Zanskars, again, we have 24 flood events. So given the chronological errors, probably the upper and lower Zanskars were connected, and they are representing the similar flood chronology. So between 15 to 6 K, we have 27 flood events recorded in Zanskars and in lower Indus. So this is upper Indus means just before the confluence of Indus and Zanskars. So there are 18 flood events recorded. In the lower Indus, from where the Zanskar meets, we have all sounds of 30 flood events. So meaning thereby that Zanskar is actually compounding the flood histories, flood magnitude, flood frequencies of the Indus. So Zanskar is actually, the headwaters of Zanskar lie in the monsoon zone, monsoon-driven systems. So that's the reason it receives large amount of floods, larger numbers of floods and that's how the flood gets compounded in the lower Indus. So if we see the flood histories, flood chronology, this is the flood chronology, and we can see that there are 3 peaks, and this is the chronology of the Hertz, so human presence in Ladakh. And this is a climate record from the very vicinity, a lake called Pangongso, and how at all in China they developed a good this climate record. You see that the monsoon picks up from around 15K or 10K, and then you have monsoon stability, and then around 2,000 years, it just becomes arid. So aridity in Ladakh is rather very newer phenomena. The first phase, 14 to 12K, second phase, 10 to 8K, and third phase is 7 to 4K. The interesting thing is this: as you start building the monsoons in the drier zones, the human presence keeps on increasing. So the human inbound migration, whenever you have strengthened monsoon and the drier zones of the Himalaya becomes greener, they become the greener pastures for the inbound human migrations. This is one of the first order interpretations. And these 3 phases are very well corresponding to what we see in the lake system. Another thing which we see, that if we see the eastern systems, if we compare these records from the eastern systems, say Yellow River and Yangtze, all the chronologies are lying just before when the Indus is started to drying. So the East Asian monsoon-driven systems has a kind of a seesaw relationship with the Indian summer monsoon system. This we knew. I mean, there are contradictory records in geology and the modern observations. Some of the observations say that they both work, I mean, they are in tandem, but many of the records also say that they are having a seesaw relationship simply because they are fetching their moisture from a very different pools. Indian summer monsoons rises from the Indian Ocean, whereas East Asian summer monsoon rises from Pacific and has a different jets and other things controlling the rainfalls. So the second message is this, that the 2 rainfall systems may have a very different signatures in terms of flood frequencies. So phases of warming strengthen the Indian summer monsoon, inbound human migrations in the drier part of the Himalaya, inverse relationship with the East Asian monsoon systems. Similar thing we see that just this is the lake delta of this Pangongso. So this delta was prograding until 1.1 Ka. The progradation means the lake was continuously going down. That's how this delta was prograding. And this is the signature that soon after this, the whole incision took place and the river started, lake started building up. So this drying of Indus system is also reflected in the lake systems, in the lacustrine systems. And we could see that on the top part of the strands, at the highest strand, we have this gastropod called radix with a freshwater, which is a freshwater species, and whereas the modern lake is saline. So in just 1,000 years, whole lake turned from freshwater to a saline system. So this is the impact of the 1,000-year aridity in this area. Interestingly, in the southern front, we do not have many records, but we explored one lake system which suggests that human presence started at around 8K. This is from the sedimentary DNA. And we have a physical presence of humans around 3K in form of the archaeological, prehistoric sites and paintings and other things. So physical presence is from 3K, but the biomolecular presence we could trace back to 8K. This has an important message to be conveyed. In the drier part of the Himalaya, you see that monsoon-driven inbound migration started having at around 15K or so. Whereas in the southern front, where the rivers are monsoon-driven, they were more volatile post-glacial monsoon optimum. That's the reason inbound human migrations was restricted until the rivers got incised. So at around 8 to 9K, the river incision started, and the terraces came into being, and that's probably the result of that resulted in the inbound migration of humans in the southern front. So you see that even these transect scale topography is deciding what will happen to human migrations. So flood histories, continental scale geomorphology, and how they interact with the monsoon system is actually deciding where to live and where to go. In terms of the sediment erosion, we happen to do some zircon uranium-led geochronology that informed us on what kind of erosion and what are the hotspots of the erosion in the Indus. We found that more than 70% of the sediment is being contributed by this Himalayan crystallines. So in the drier part of the Himalaya, it is the core of the Himalaya which is being eroded most when the floods are in the context of floods, right? So the message take home so far is that Indus is having the flood histories preserved from 15,000 years to present, and the aridity in Ladakh is very young, less than 1,000 years, and the lakes and the river systems are representing both, and human inbound migration took place in tandem with the flood frequencies. Now let's just see the mid-Holocene mega flood records, or in the Sangpo or Brahmaputra or Siang, what we call it. It is Sangpo in this area, then Siang in this, and mountain front, it's called Brahmaputra. So this is the catchment, and this is the topography, longitudinal scale, profile. See, these are the areas that we sampled, and we have several published records from this area. So I'll try to give you all-inclusive picture here. See, these are the sections which as I told you, these are one flood events. We do not have any couplets here. So this is one event. So we dated them using luminescence, as we didn't have, because there are no settlement surfaces. So we could not find any in situ charcoal in these areas. So we dwell upon luminescence dating technique here. The sediment provenance, again, was characterized by using petrography and some isotopic signatures, and we found that most of these floods were actually originating on Tibetan Plateau. They were exhuming a whole lot of sediment from the syntaxial bend, and then they were depositing. So the floods originated in Tibet, and flood waters entrained large amount of sediment from the northeastern syntaxes. This is the major conclusion from the sediment provenance, because the Tibetan Plateau has a altogether different sedimentary profile, and syntaxis has a deep, extruding or exhuming crystallines. So these two different rock types are very much traceable in the sediment budget of the systems. So that's what we did. So chronology, I'm sorry to show you this table, but it was important. You see that there are several floods, and one of the flood is 7 into 10 power 1.7 to 10 power 7 cubics of discharge. This qualifies to be called as a mega flood, and it's one of the largest ever flood recorded in any river systems. So the mega flood category flood occurred in Himalaya in the eastern part, just in the human time scale. Upper Harappans, or they were living there. So in the human time scales, you can have these kinds of floods. So why not today? So you see that the chronology from this area, you see this is the chronology of flood deposits. This is the chronology of all the lakes and other moraine deposits from these. So most of the peaks, they actually correspond to the lake forming events in Tibet. So when the lakes are formed, this warming occurs, these lakes breach, and they compound the flood magnitudes. They supply huge amounts of sediment, and that's how the flood magnitude in Indus is decided. So again, it's a topography, it's a reach of the monsoon, and the post-glacial systems that are there is deciding the magnitude of sediment supply, magnitude of the flood supply. So in conclusion, the large floods of 10 power 4 cubics in Indus occurred during the wetter phases in the post-glacial warming, whereas this eastern counterpart has mega floods, experienced mega floods in the same regions. And the sediment supply was basically controlled by the core of the Himalaya, that is higher Himalayan crystallines, and that's how the exhumation and deep earth surfaces, so deep earth processes and the surface processes are coupled. So we now know something better than before, that the damage zones of the floods are predictable. Water and sediment routing are now actually, most of the river systems are known, so we should be able to lay our hands how to protect these systems. Unfortunately, this is the word cloud, when the word flood was typed in this. You see, there is nowhere geology actually comes into picture. It's all the peripheral things: disaster, environment, discharge. Nowhere you cannot see geology. So I do not know what kind of models are existing, but until and unless you understand the geology, I doubt that anything concrete will come out. Interestingly, but just last week, we found that this paper is coming up. Citizenship is the determining factor of geoscientist career. So it's not only the geoscience knowledge, there's ethnicity that is also bringing in some bottlenecks in terms of the sediment, in terms of the knowledge flows and in disasters. You see that this is again something a global south phenomenon. So ethnicity, lack of knowledge, lack of empowerment is actually the major forcing factor of disaster that forms a disaster actually. Otherwise, it's a natural phenomenon, and it all can be understood, it can be mapped, and it has a sense of predictability. These are the type of students that contributed to this work, and I thank INCOA, I thank INCOA Roma for inviting me, and yes, it's time to change. Thank you.
Thank you very much. And now, as you know, we move to the poster session and then lunchtime, and we reconvene at 2 o'clock for the General Assembly and the closing ceremony. Thank you very much.